in this Annual Technical Conference 2023. We are about to start the first inaugural GNG session, and for that I would like to request our esteemed chairperson. First of all, I would like to invite Mr. Zahir Alam. Sir, can you please come on the stage? I would also like to request Ms. Shazia Talat to please come on the stage. Please, ma'am. Before starting the session, let me give you a brief introduction about our chairpersons. Mr. Zahir Alam is a seasoned professional, having vast and diversified experience spanning over 35 years, managing upstream and midstream oil and gas sectors with both government as well as multinationals. He is presently leading all technical functions at UEP as Vice President. Before that, he led the Exploration Department of UEP, besides spearheading regulatory and business function at BP Pakistan. He spent his initial life at Ministry of Petroleum and Natural Resources, where he served for 18 years, including in the senior positions of Director Exploration and Director Gas, playing key role in regulatory and policy matters. He also worked on cross-border gas pipeline deals as well as LNG policy. It's an honor, Zahir Saab, to have you here. Ms. Shazia is the General Manager in Exploration Department of OGDCL. She has been working in OGDCL for the past 31 years. By profession, she is a geophysicist. She did her MSc in geophysics in 1989 from Quaid-e-Azam University, Islamabad, and joined OGDCL as trainee geophysicist in 1992. During 2 years of extensive on-job training, she worked in 2 seismic data acquisition crews, as well as in the Data Processing Center. In 1994, she joined Prospect Generation Department of OGDCL. Since then, she has worked in various positions in the company, as well as different geological basins of Pakistan, and have been part of numerous fields discovered in the lower Indus Basin. Presently, she is looking after all activities in OGDCL's exploration licenses. It's an honor to have you here, ma'am. So, before starting the presentations, I would like to have some note for all the presenters. The time of presentation is 20 minutes. And after 20 minutes, the bell will ring, in which you have to conclude it as quickly as possible, because there are all the slots are completely filled, and it would be very difficult for the others to complete in the given time. I can completely understand that all the presenters will be presenting with a valuable research, but we have to give way for all the presenters to come here and show the research, showcase the research. If anyone has any detailed work, we can always arrange a special session for that person. So please cooperate with us. Thank you. So I would like the first presentation to please start. I would like to request Mr. Adil Azim to please come on the stage. Mr. Adil Azim will be presenting Predicting Subsurface Petrophysical Properties and Characterizing Reservoir Using Rock Physics Modeling and Iterative Petrophysics-Driven Inversion Results. So before I hand over the mic to Mr. Adil Azim, let me introduce you, give me a brief introduction for him. Adil Azim is a senior geoscientist in MPCL. For more than 13 years, he has been running and leading reservoir characterization studies. Mainly, his interest lies in pre-stack inversion, multi-azimuth seismic interpretation, rock physics modeling, 4D interpretation and analysis. In MPCL, he is performing a number of reservoir characterization projects. Professionally, before MPCL, he has been associated with North Oil Company Qatar, OMB Pakistan, and OPL Pakistan. He did his MSc Geophysics from Quaid-e-Azam University, Islamabad, with distinction in 2010. So, Mr. Adil, I would now request you to please start your presentation. If you need any mic, you can always get.
Yes, for sure. Thank you, Samad. Thank you so much. Good morning, everybody. So, before starting the presentation, just let me tell you a little story. So, the year was 2016. I was in the similar arena right across the room, presenting my first paper on quantitative geophysics. I finished my paper, and then after that, my mentor came up to me. He patted me on the back and said, "Good job, Adil." So that was quite amazing because it led me towards going towards that quantitative geophysics side that I've never would have done before in my life. And now, why I'm telling you this story is because this room, this arena is filled with experience. So if you're a young geophysicist, geologist, engineer, maybe it's time to find a mentor. And if you're a little bit having gray in your beard like me, maybe it's time to pat somebody on the back. So this will have a great kind of a experience for the young person to have that kind of a mentorship to him. Maybe after this presentation, I will like a pat on my back as well. So let's start the presentation. So my topic is quite hefty, but I will try to keep it short and specific to the topic. You know that most of the companies have this kind of a problem where they are trying to get the most accurate petrophysical properties. So what we have tried to do in this particular study, we've done just that, tried to predict the accurate petrophysical properties. How we did that? So I would tell you about around a 10 steps rough workflow that would go through, that I would go through in my slides, where you would know how to predict the petrophysical properties and the lithophysies coming from the seismic inversion. And those are the derivatives that would actually come from the pre-stack inversion. And where is the most important step in that whole jigsaw puzzle that we will discuss in a bit more detail. So why would we do reservoir characterization, pre-stack inversion? Why would we waste our resources? Maybe not waste, maybe put our resources into that. This is the statistics that are in front of you. So Westwood Group, what it did was for the last 13 odd years, from 2008 till now, there have been gathering the data of different discoveries. So out of 220 discoveries that were made worldwide, commercial or non-commercial, 78% of those discoveries found lesser volume than their pre-drill pre-50 volumes. Just imagine, this is a big number. So what has been happening for the past decade? We have this, I think all of us, we have this knack of predicting or maybe predicting the reservoir properties and the reservoir size a little bit bigger pre-drill. And once we drill that, it's obviously not that optimistic anymore. So the reservoir characterization in that particular equation is very important. So you can have the size of the reservoir, which is quite important, the size of the accurate size of the reservoir. And then consequently, the volume within that reservoir would be more accurate if you have done a reservoir characterization study. So it's very important for your whole E&P life cycle to have that kind of a study in your pocket to go forward with your exploration or production strategy. So coming to the detailed part of this presentation, where we have actually used a data set coming from the study area, which lies very familiar to some people in the Middle Indus Basin. Our study area lies right on top of Madikand Kothai. The stratigraphy that we were dealing with was very familiar to everybody as well. It's Lower Guru Sands. More specifically, when we talk about Lower Guru Sands, in this particular study area, we are talking about B sands. We had 5 wells at our disposal, where 5 wells had elastic logs available. You can see the list over there. All the elastic logs were available in all of the wells. But more specifically, one of the well had the full suite of the elastic logs. So that is quite important because that is going to be a little bit of in the upcoming slides. That is going to be quite important that only one well had the full suite of logs available. Also, the quality of those logs is also mentioned over here, which logs are more affected by the borehole conditions. Those are shown here with poor or fair quality. When you don't have that kind of a borehole effects on the logs, they are shown here with good quality. Other than that, for this pilot study, we had around 60 square kilometer of seismic data available, which was obviously pre-stack data for seismic inversion. So my workflow that we use for this particular study is quite important because it has those elements which are basic elements which are very important for any reservoir characterization study or a pre-stack inversion study. So starting from well log conditioning, then to seismic petrophysics, rock physics, those are the building blocks of any inversion study. Then validation through seismic, that is one of the steps that we are going to present in the upcoming slides. That's very important once you talk about any kind of a well data that is being modeled from the well logs. Then once you have all of the data set, all of that well ties you're happy with the well ties and everything, then you go for the wavelet estimation, and then the step is quite easy. Then you go to your pre-stack inversion, deterministic inversion, stochastic inversion, and then there comes the derivatives of those inversions, which are in lithofacies, porosity, etc. This slide would actually stress upon that particular point that I talked about, the building block of any reservoir characterization study. So starting off with well log conditioning, very important. We have to do specifically the density data. It's affected by the borehole conditions. We have to really go through the whole data set, see if there are in depth shifts, any kind of a borehole issues related to normalizations as well, because if you're using different muds and different well bores, you would have normalization issues specifically to gamma ray. Once you're happy with that, then go to seismic petrophysics. Seismic petrophysics is a little bit newer word for, let's say, conventional petrophysics, where you're actually not only dealing with the reservoir itself, but you're also doing petrophysics on the shale bodies that are present in the rock as well. Rock physics modeling, where you're modeling the rock from the scratch. You're trying to see what is the mineral makeup of the rock, and then trying to see how that mineral makeup of the rock is going to show the elastic properties. You're not inputting the elastic properties, you're actually predicting those elastic properties through a rock physics model, a physical rock physics model. For this particular study, we have used inclusion rock physics model. Then the seismic validation, which actually includes the seismic well to tie. Then you have AVO analysis that we are going to present in this study as well. You see those arrows coming down and then going up as well. This is the key in this overall workflow, the top part of the workflow that I showed. The iteration is the key if I need to summarize this. So if you're not happy with, let's say, well conditioning in the seismic petrophysics part, you have to go back. If you're not happy with the rock physics model, once you have done all the 2 steps, you have to go back. So iteration is the key. Once you do iterate your overall workflow, you will be able to get to a result which is reasonably good. So once we did the rock physics modeling, what we are trying to do is making a physical model. From the physical model, we are trying to extract the elastic properties. So that's what we have done here. In this particular study, we had an upper shear interval and a lower shear interval. Lower shear interval has those sand bodies as well. The upper shales were a little bit less compacted. The clays in the below section were a bit more compacted, so we had to use different rock physics models and different rock physics parameters for those 2 intervals. In the red, you see the logs which are actually predicted from the rock physics model, and then in the black, those are the logs which are actually recorded logs. And this is the point for any reservoir characterization study. We are going to use modeled logs for our inversion study rather than the recorded logs. So this statement is like the key for our study that we have done over here. So why do we do that? It's here. So on the left-hand side, you have the elastic domain cross plot, which is the best friend of any geophysicist. So you have VPVS and P impedance. You see the recorded log on the left, and it's colored by the gamma ray. Everything is overlapping. Your sand is above shale is behind sand, you don't see a shale trend, and also you see some non-physical VPVS value going below 1.414, which is non-physical for any rock. If you take this recorded data and do any kind of pre-stack inversion, you would not be able to get any separation between sand and shale. You won't be able to have any separation between your reservoir sands, which are filled with gas or oil, and your brine sands. Once you take it through a rock physics model, that's on the right over there, the picture in the middle, you see the brine sands trend is quite good. It's physical. Then you have the gas sands trend, very nice over there. And also the shale trend is quite good. I'm sorry I'm not using the pointer because it doesn't show over there. So I'm trying to convey the message through talking over here. So this is only one well. Once we put all of these wells through the rock physics model, that's the picture on the right over there. Every well which didn't have any shear wave information in there still is plotted over there with VP, VS, and P impedance. Quite important because once you don't have the shear wave, you try to get it from any kind of multilinear regression. You try to do it from any kind of machine learning approach or any kind of linear approach or empirical models. But here we are getting the shear waves from the physical rock physics model for all the other wells. And it is going on the same trend. The shale trend is the same as the first well. The sand and the hydrocarbon sand trend is the same as the first well. So the rock physics model is quite consistent all in the area. The below pictures are actually giving you the same idea that how the rock physics model logs are much more better in differentiating your reservoir sands from your shales. And if you're trying to build a shale model itself for a, let's say, a tight gas sand kind of a play, or maybe shale gas play as well, this shale gas trend will give you all those sweet spots for the shale gas as well. Then on the right-hand side, we have a QC plot, which tells you there is no linearity in the plot, and it is actually showing you that the petrophysics itself didn't have any hard cutoffs in it. Once you come to the validation part of the seismic, on the right-hand side, you have that correlation coefficient between your recorded data and your rock physics model logs. So you see in every well, the correlation coefficient overall at zero incidence increased as we went from one well to the other if you use the rock physics model logs as compared to the recorded logs, with exception to one well which had a very small logged interval. On the left-hand side, that's quite important. So for the geophysicists, this is kind of a Bible. So AVO of any rock or any particular reservoir interval is very important. You have to keep the AVO consistent through any processing. So on the top, we have the raw seismic and some angle stacks, and also you have the process seismic. All of them are showing class 4 anomaly. The gradient is, as you increase the offset, the gradient is also decreasing, so in the decreasing trend. And on the bottom, what I've tried to simulate is the same thing that I talked about in the previous slide. When you don't have the shear wave, you try to get it from multilinear regression, linear regressions, or maybe you just use the original data itself. So once you do use the multilinear regression, which is shown in the blue, it doesn't follow the same gradient as you see in the original seismic. If you use the orange one, which is from the original logs, the recorded logs, it has a totally different gradient as compared to the original seismic. And only the rock physics model logs are consistent with the original seismic that we have. So if you don't put a consistent data into your inversion model, you shouldn't be expecting good results, obviously. This is another QC. We try to do the QC on the recorded logs versus rock physics model logs as well, when we try to extract the wavelet at every central angle. So at every central angle, our wavelet was more smoother, the phase was less, and we were able to get a very nice wavelet that is ready for inversion. But another noteworthy thing is that recorded data also showed some data below 10 hertz. And as you know, the ground acquisition we don't have, usually don't have under 8 hertz, we don't have any data. So that data is actually low frequency noise that we are actually adding into that particular data set. So we don't have to use the recorded wavelets for our inversion analysis. So I think I have put my point very firmly that recorded logs are inherent of all those noises that we experience in the borehole, and physical rock physics models is the key to go. Don't know, it's taking a bit of time to process my, going to the next slide, sorry. So now, this is where it's called the graveyard of pre-stack inversions, this slide, because most of the projects actually die here. Because you're not using, in any of the inversion projects, you're not using petrophysical logs, you're just using elastic logs, going for the low frequency model, going for inversion, and then at this point in time, this is the first time that you see the petrophysical logs. And when they're not talking to each other, you don't see a picture like this. It is overlaid with, the shale is overlain by sand, sand is overlain by shales. But here, because we have that connection right at the first step, where we connected the rock physics model to our recorded logs and then created the rock physics model logs, and then we have a connection between the petrophysical properties and the elastic properties. And you see on the left-hand side in the cross plot of P impedance versus VPVS, the sand is totally separate and the shale is totally separate. The probability density functions that we made for these particular sand and shale model were very good, because at the bottom there in the confusion matrix over there, you see that all the 91% of the samples of the sands were classified correctly, and 98% of the samples of the shales were classified correctly. If you put this data into your model, then you will be able to get good results. On the right-hand side, you have the deterministic inversion on the top, and the bottom is the derivative of that pre-stack inversion, deterministic inversion, where you see sand and shale. Although it's good, you see the sand, you see the shale, but we were not happy with this, because the resolution of this didn't allow us to go directly into the simulation models, because everybody knew that there is sand there. We wanted to know, how is the shale behaving between those sands? How is the one sand connected to the other one? So for that particular problem, we went to pre-stack geostatistical stochastic inversion. So on the left-hand side, you have those all cross plots, which are showing you on the top over here. Okay, it's showing something. Okay, good. So on the top over here, so the depth in the depth domain, you see all the data set over here, where you have the shale trend, where you have the brine sands, you have the gas sands over here. If you turn it into time domain, you already lose the frequency over here, you see. So this is like 2 millisecond or 1 millisecond, every sample in 1 millisecond. Once you turn it into a 40 hertz, let's say, data set, it loses frequency again. Still, you see the trend. And that's what this inversion, this derivative of the deterministic inversion on the bottom right is showing. What we're trying to achieve is something like this, something between 120 hertz, maybe a little bit more, where you have a sample of lithofacies or maybe porosity at every 4 millisecond or every 2 millisecond. So that was what we were trying to achieve. For that, we had to build some horizontal variograms. And we were very lucky to have like 4 or 5 wells in the same area. We were able to build a horizontal variogram. Maybe it's not a good idea to build horizontal variogram when you only have 1 well or 2 wells. It's better if you have more control when you build that horizontal variogram. The result of that is on the top right. So on the top right, what you see is the most likely facies from a stochastic inversion. You build a model, you do like 100 or 200 iterations, and what you do is, at the end of the day, you kind of merge or mean all those iterations and have a most likely facies that could be a more realistic picture of your subsurface. And here you see there is much more detail as compared to the lower part over here. And with this study, we were able to see which sand was connected to which sand and where was this disconnection. And for this particular study, because it's a stochastic inversion, we were able to build probability maps for each sand body separately, and this went directly into the simulation model. So that's quite important. So at the end of the day, we are trying to find where the uncertainty related to each sand body, and especially the distribution of that particular sand body and how they're connected with each other. Another petrophysical property, which is usually we use the zero offset or P impedance directly to do the estimation of these porosities usually, but with this one, it also shows once you do your geostatistical inversion, and specifically once you do your geostatistical inversion using the rock physics model logs, you're able to increase your prediction of the porosity away from the wells with a higher coefficient. It's almost 94%. It looks unreal, but it's real. Yes, geostatistical inversion has that very fine resolution that we were looking for. But if you go with the deterministic inversion, it's still good. It gives you around 85% of correlation coefficient with the actual porosity and the predictive porosity. So we did this through probabilistic neural networks. So probabilistic neural networks has that validation error. So we made sure that the validation error for this particular example is really, really low for the attributes that we use. So if you see the number of attributes that we used for the deterministic inversion, we were only able to use 5 attributes. But once you did the geostatistical inversion, you were able to use 8 attributes. So that's the main reason for increasing in the correlation coefficient of the predicted porosity. So on the sections over here, at the top one is the geostatistical inversion, where you are actually seeing much more resolution as compared to the deterministic inversion at the bottom. So if you use this and take it directly into your simulation model, you would be able to see porosity values away from your wells, and would see some sweet spots, or maybe you won't see some sweet spots, or you would see the actual dimensions of your field. And that was my point when I started my presentation, that why 78% of the discoveries found less than P50 volumes. It was actually the size of the reservoir. We were predicting the size of the reservoir more than it is in the subsurface. So if you are trying to develop a field development plan for a particular field, I think this is the way to go. Do some geostatistical inversion and start with rock physics modeling. Manually kar dein. So at the end, I've said all these points in very details. Rock physics model is the key to the success of any pre-stack inversion study, because it creates a bond between the petrophysics and the logs themselves, the raw logs themselves, at the first go, that you don't have to create afterwards in the process of your pre-stack inversion. Consistent model is really good because you're able to predict the reservoir properties or the logs away from your known points, and it has to be a consistent model that I showed in one of the slides. Seismic validation, again, is quite important, because seismic is something that is maybe a little bit less affected on the resolution scale as compared to the borehole logs. So seismic validation for any kind of pre-stack inversion study is quite important. Once you use all of that, you would be able to get better results. And then you have to choose. If you want a deterministic inversion, where you just want to see something away from the wells, deterministic inversion is quite good. But our objective was, for this particular study, was a little bit more. We wanted to see if the sands were continuing in a certain direction or not. So we went for a geostatistical inversion. So might be an overkill for some of the studies, but this is how the whole process went through, and how our thought process went through. So at the end, I would like to thank the management of Mari Petroleum for allowing us to publish this data set. It's quite important for us. Special thanks to all the technical leads and the technical team of Mari Petroleum for giving us this opportunity, and really inputting very valuable comments that actually made the paper that it is right now. And special thanks to ATC committee, the chairpersons over here, which have guided us through this whole journey of this paper. But at the end, before I finish, I wanted to leave you with a certain message for this paper. So for the rock physics model, that's the basic step. So if you get the basic step done, and then you go into the inversion, you will be able to get relatively better results and reasonably good results. So if you're not doing that particular first step, then you shouldn't be expecting anything good at the end of the pre-stack inversion. So if I can summarize my whole paper in like a couple of words, it would be get the basics right. So thank you so much, everybody, for your time and attention.
So, are there any questions for
Yes.
the speaker?
Yeah, we only take 4 questions just for the time constraint, so you can ask question. Yes, Mike. Mike.
First of all, I like to congratulate the way you presented. It was nicely done and
Thank you.
very nicely explained. I have a questions, and just for my sake of my information, one of the things which I've realized that you're talking about the rock physics modeling and AVO analysis in the reservoir in the known field, right? It's already with the 5 wells with reservoir is quite known. So basically, this is a generalized workflow of doing the rock physics modeling, right? So number one is that something you have introduced a new thing in it, which is unique? Because this is the entire process is well known and well established. And if you have added anything additional that can help all the other people sitting in this room who can learn, I want to know about that one. The second thing is that you haven't shown the reservoir flow units against the rock physics model. And also I haven't seen the fluids properties, which is the key thing, because the main emphasis is on the extension of the sand bodies, not the fluids.
So to answer your first question, what I've seen in my overall experience, that there are certain rock physics model, I would say in quote, there are some rock physics models done, and those, quite frankly, they are multilinear regressions. They are not rock physics models. Once you build a physical rock physics model, that gives you a more realistic view of the recorded logs and your physical rock in the subsurface. So our paper generally wanted to highlight that point, that petrophysics and rock physics have to go hand in hand. And what we have seen practically in different studies, I've seen myself in different studies, that connection at the first hand is not there. So this is something that is there in the industry, but I think it's a bit neglected. That's why we wanted to present that as a study. So it's not something new, obviously, but it's something that is neglected more often than we should have done. The second question is about the flow units, and this is a kind of a pilot study for the Mari Petroleum itself. We want to extend this to other areas where we have less wells, maybe 1 or 2 wells. We are trying to do that right now. For this particular study, we are trying to extend this study to different other wells, because we don't have like 6 wells there, we have more wells in that particular area. We are trying to extend that in the same area in that particular model as well. So I think next year maybe you would find a paper where you would see all those flow units correlated to this pre-stack inversion. So thank you. Any other questions?
Itsham Faisal from United Energy. It was a wonderful presentation you have presented.
Thank you.
I was a bit curious about, by inputting logs inside, especially the shear log, that is very important piece of running this whole model. So once you're able to validating that piece, I think the demonstration in the form of cross plot will help you more to understand your model versus the original log which is being acquired in the wellbore. That is something which I think we are not able to see in the presentation. That's the first piece. The second question, I just want to understand, you showed us the validation of seismic in the form of AVO cross plots. Basically, with a certain percentage of hydrocarbon in the system will also give you a AVO effect. So how you are certain to show us, I mean, this is a saturation of above 50%, or let's say 60% of hydrocarbon in the inside the system you have it, but it is not an effect of 5 to 10% or 2-3% of hydrocarbon. So maybe these are the two particular questions I was thinking to ask to you.
Thank you so much for your comment. First of all, we try to see the shear part of that in VPVS domain. We try to show that, but in the particular paper or the journal that you would see in the printed form, you'd have more examples there. So with the time constraint, I didn't put them here, but a QC plot was there in one of the slides where we had the shear wave logs with the porosity. That was the biggest QC plot for any petrophysicist to see if we are cutting something or we are putting linear information in there. So there is no linear information. The second one about seismic validation is quite a good point because AVO itself is dependent on a lot of things. What we are trying to see is only the gradient analysis, not the intercept itself. We are trying to see if the gradient is altogether different in some particular, let's say, data set. For example, in multilinear regression, it was going altogether the other way. In the same scenario of in situ, in the same scenario of the frequency, everything similar. If it's going the other way, it's definitely something wrong with the logs. So what we are trying to do is more of a qualitative kind of a seismic validation on AVO, but more quantitative is towards the side of the seismic correlation coefficient at each central angle. So we used 5 central angles, where at each central angle, the correlation coefficient increased as we use the RPM logs as compared to the original logs. So that gives us more confidence that in terms of quantitative, it's increasing as well. And in terms of qualitative, it's more relevant to the AVO response that we see in the original seismic. Thank you.
Any other question?
Akhtar Masood from UEPL. It's an observation that you have one well where you have the shear data. And you said that we have predicted from the MLR and the neural networking. So what do you think by having a one shear of the one well for the 5 wells? What's the certainty of this, and which one is the better method for this prediction, either the MLR, machine learning, or the neural networking? So what's your suggestion? And second, if you have a frontier areas, how would we relate this study for the upcoming fields? So thank you.
Specifically for shear is a byproduct of rock physics model. It's not the primary product of the rock physics model. So if you're confident on the parameters of setting the rock physics model parameters, I think the best way to have a byproduct as a shear wave would be a rock physics model, not MLR, not machine learning, not neural network, because it has limitation to the data set that you input into it. Rock physics model doesn't have that limitation. It is more predictive. So if you find a certain shear wave parameter here, it would predict it away from the well as well. If you find another well, it would be very similar to what you see on the rock physics model. So if you have a consistent rock physics model of the area, I would always go with the rock physics model to see the byproduct as a shear wave. The second thing about frontier areas where you are trying to see, for example, if you're doing a dry well analysis, or if you're doing to see the extent of a certain discovery, it's very important that you build a rock physics model. For that, obviously, you would need shear data, you would need good density data. That rock physics model will help you to see on the seismic, away from the seismic, where those sweet spots are, or maybe why your well went dry, and so on and so forth. So even for one well, there is a possibility of doing a rock physics model, and its prediction is very powerful.
Thank you.
Thank you.
So I saw another hand here. This would be the last question.
Yes, my question is related to iteration. As you have said that the main thing here is the iterative process. So is the iteration is manual, or is there any automated process through which you can iterate the rock physics model or the petrophysical properties?
Yes. So for this particular study, we used a specific software. I don't want to name the software, but the iteration is very easy in that particular software, where you can do the petrophysics on the go and then change the parameters somewhere in the rock physics model and see how it affects the approximation of the elastic logs away from the wells, or maybe on the well that you're trying to achieve. So it's quite intuitive and it's very fast. So you just go through petrophysics to rock physics in one go, in one window. It's not a operation that you have to go manually, put the logs in one software and then run the petrophysics and then go back to another software where you put rock physics model. So it's very iterative process in the same window. You can do it. There are different softwares that do it, but I think where you have, if you don't have petrophysical connection in any software for rock physics modeling, I think you should run away from that software. So that would be my message.
Thank you, Adil. Wonderful paper. You and your co-authors have done a wonderful job helping us understand rather building the bridges between the petrophysical and the rock physics stuff. Try to understand how to expand the knowledge that you gain from drilling of the well, trying to really get with the kind of like a rock physics model developed. I think you share your experience with the audience, and I hope that they're going to really learn from it. Thank you very much.
Thank you so much. Thank you.
So I guess the next presentation is on developing the depletion strategy of the structurally complex downthrown oil field through improved reservoir characterization and static modeling. This is going to be presented by Binish Aslam. She is working at UEP as a reservoir geoscientist. She completed her master's degree in geophysics from Bay Area University, Islamabad, and she has been associated with UEP since 2019. Over to you, Binish.
Thank you, Zahir Saab. Assalamu alaikum and good morning to everyone. Today, my name is Binish Aslam, and today I'm going to share with you a depletion strategy that we developed for a structurally complex downthrown oil field, and we achieved this. We achieved this through improved reservoir characterization and static modeling. For this project, I had the pleasure of collaborating with Hassan Ahmed Khan, Musab Abdur Rahman, and Shadab Ali Qureshi from within UEPL. Apart from that, we also had support and suggestions from our joint venture managing partners from GHPL, Atikur Rahman and Abdul Basit. I would really like to thank them for their input. Next slide, please. Okay, so today I'm going to discuss with you I will give you a brief introduction of the study area, which will include the geology and tectonics. Then we will have a brief inventory of the database that we had available for the static model. Then I will discuss the methodology that has been divided into the conceptual model, the fault model, and the structural model. I will also discuss briefly how we have done petrophysical properties estimation. This will be followed by how we did rock typing and water saturation height functions. The petrophysical property distribution will also be briefly discussed, and I will then end and conclude the presentation with the results and the way forward that we have adopted as a result of this static model. So the area that we have under study is pretty well known. It is situated in the Lower Indus Basin, which is an extensional regime. The Lower Indus Basin is a well-known and prolific hydrocarbon producing basin of Pakistan. The major geology and tectonics of this area are affected by the continental rifting that occurred between the Madagascar and Indian plates sometime between mid to late Cretaceous. So because of this rifting events, the common structural styles that we find within these areas are anticlines, thrust faulted anticlines, tilted fault blocks, and hoist and graben structures. The source rocks that are prominent in this area are from the shales of Lower Guru and Sambar formation, while the reservoir formations are mostly from the Lower Guru formation, and within this Lower Guru we have the upper sands, middle sands, and the lower basal sands. While shales of the Upper Guru are acting as cap rock throughout the region. And the hydrocarbon type that we find within Lower Indus Basin is also from the oil and gas. So you can see on the right side that the field is located on the downthrown side of the main fault. Before this, when exploration started in the Lower Indus Basin, the dominant reservoirs that we find are usually situated on the upthrown side of the main fault blocks. But after exploring those reservoirs, those fields, now that we have exhausted all of them, we are now moving towards exploring and developing the downthrown sides of the main faults. Okay, so this is the alpha field that I am going to discuss with you today is producing oil from the upper sands of the lower groove formation on the downthrown side of the main fault. This is a generalized stratigraphic column for the lower Indus Basin. Here we can see that the source rocks are mostly from the late Jurassic to early Cretaceous shales, and the reservoirs are within the early Cretaceous lower groove formations. And the shales that are adjacent to these sands are usually acting as the seal for this. This is a, this here is a, this is a cross section across the lower Indus Basin that is showing the regional structural styles that can be found in the area. So now coming to the study area that I am basically presenting today as my project, because we are developing, this was a field that was situated on the downthrown side. We were experiencing two main challenges with this field. First of them was that because of intense faulting, there was compartmentalization across the field, and this is a challenge if you are trying to produce oil from a compartmentalized field, because the oil is trapped in different compartments. So you have to really understand the compartmentalization across the field to have an idea and produce optimally from that field. The second challenge that we had with this was the reservoir heterogeneity. Reservoir heterogeneity we were experiencing because of greater overburden because of being situated on the downthrown side of the field. Apart from that, some diagenesis processes were also contributing to the reservoir heterogeneity in these downthrown fields. So and these two challenges were producing two problems for us. First of them, as I discussed, it was that we cannot optimally produce oil field if we don't understand the compartmentalization. And the second one is that if you have reservoir heterogeneity, the estimation of in-place numbers becomes very uncertain. So to have a more certain in-place number, it was better to understand and capture the reservoir heterogeneity. So for the mitigation of these challenges, we adopted two strategies. One of them was to have reservoir characterization. This was done through rock typing across the field that divided the whole reservoir into different rock flow units. And based on that, we were able to understand and evaluate our reservoir more. The second strategy was to develop a static model. This static model was built so that we can understand the placement and the communication across the splay faults that are present in the field. So for this project, the database that we had from the geological side, we have 7 wells across the field from north to south. And we had wireline log data from these wells that was processed for the petrophysical estimations. We also had FMI data in one of these wells that was used to confirm the dip of the main field bounding fault. Apart from that, core data from one well, Alpha-1, was also utilized for the RC analysis and sedimentological core study. And from the geophysical side, we had horizons interpreted from the seismic, and we incorporated the splay faults that were visible on the seismic section. So for the methodology, the first step that we took was to build a conceptual model. This conceptual model was very important to build because without this, to understand the reservoir heterogeneity would have been very difficult. For the building of this conceptual model, we were relying on two studies. One of them was from the core sedimentological study that we carried out on Alpha-1 well, and another was a regional study that we had done for the reservoir to understand the environment of deposition for different reservoirs. So the regional study that we conducted indicated that the dominant environment of deposition for B sands is shallow marine, where the reservoirs are usually deposited along the shore face settings. So here you can see that at this point, these areas are basically tidally influenced channelized deposits, which are deposited as a result of interaction between tidal and fluvial processes. Another deposits that you can see here and are producing from B sands are these tidal sand waves, and these are what we have been targeting in our alpha field. These tidal sand waves are deposited parallel to the shoreline, and they have an extent of about 2 kilometers and width of about 2 kilometers and height of 1 kilometer. So they are not that extensive that you can find them very regionally. You have to really focus your exploration in different areas to understand them. And in this cross section along this sand wave, you can see that this sand wave can be divided into three different facies. One of them is the sand wave crust. This sand wave crust has bioturbated sands which are lime rich, and therefore they are not very good quality reservoirs. The second ones that we have are these sand wave flanks. These are coarse grained, well sorted, clean sandstones, and these are basically the prolific reservoirs that have been producing in our alpha field. And the third facies that we have is this sand wave margins that are basically the transition with the shelf, and these are argillaceous sandstones, so they are more rich in clay content and they are poor quality reservoirs. For lower Guru B sand in our alpha field, the main producing zones are situated from the sand wave flanks, which are the best reservoir qualities. Sorry. Okay, so the fault model was developed to counter the problem of compartmentalization across the field. As you can see here in this seismic section, this is the main fault, and we have 3 splay faults right along this main fault parallel to it. And because of these splay faults, we also have a very steep dip, and these are also producing compartmentalization across this area. And this region here is very tectonically disturbed. So many of these splay faults, as seen on the seismic sections, were incorporated into the static model. Some of these splay faults were also confirmed from the different wells that we had from Alpha 4 and Alpha 7. And FMI data from Alpha 7 helped us to confirm the dip of this main fault, that it was around 75 to 80 degrees. Okay, for the structural model, we basically developed a stratigraphic framework that was oriented in the northeast to southwest direction. This orientation of direction was taken from the understanding of B sand and environment of deposition for the B sand wave crust. Based on stratigraphic correlation across these 7 wells, the complete reservoir of B sand was divided into 7 different zones. Zone 2 and Zone 6 were the most prolific reservoirs that have been producing in this area. Pillar gridding method was used for this static model, and it was employed because pillar gridding is able to capture the topographic variations that are present because of the faults very accurately. So for petrophysical property estimation, the porosity data was calculated from the wireline laws. For permeability data, we used the RC analysis from Alpha 1 well. The RC analysis on that core data gave us an estimate that the permeabilities vary from 0.01 to 450 millidarcy. This porosity permeability relationship established at Alpha 1 well was then applied to all of the different wells through neural networking technique, and to QC the results of the neural networking, those were also correlated with the PBU analysis at Alpha 1 and Alpha 2, and they were a fairly good match. So we were confident on our permeability data. This graph here, you can see that this is the relationship established from the RCA between porosity and permeability, and this black these black dots are the data that was created from the neural networking technique for all of the different wells, and it is a fairly similar kind of trend as we had from the alpha 1 well. So rock typing. Rock typing was very important, as important as the conceptual model, because the rock typing is able to, it enables us to divide the reservoir into different distinct units, and those units are basically divided on the fact that they are deposited under similar geological conditions, and then they are also undergone through similar diagenetic processes. These two things basically define that this rock unit is going to have a similar relationship between their petrophysical properties such as porosity and permeability. They are also going to have a similar capillary pressure profile and saturation height function. And because of all these characteristics, the fluid flow characteristics of these rock units are similar. And that is what we were trying to basically achieve in our static model. And also incorporating this rock typing at the static model level, it helps that you don't have to apply, a multiplier at the simulation model. So this was very critical for us. This CDF analysis here and this porosity permeability relationship established at the field level divided the reservoir into 5 rock units. However, when we correlated this with the MICP data from the alpha 1 well, the excellent rock quality and the very poor rock quality was not present here, and therefore we upgraded or upscaled these 5 rock units into 3 rock units, and these 3 rock units were basically then distributed across our static model. For saturation height modeling, a scaled Harrison fitting function was used. This was used because this fits the curve, this fits the capillary pressure curve with the different coefficients, and it is very controlled. And the results were also verifying this, because the saturation calculated on the wireline logs was in a very good match with the saturation established through this saturation height function. So for the petrophysical property distribution, 2 techniques were used. For vertical distribution, we developed a composite vertical proportional curve and from all the wells, and this helped to understand and incorporate the vertical variability across the wells. And you can see here in this diagram, this yellow colored rock type is basically the best reservoir quality, and this is present across zone 2 and zone 6. For horizontal property distribution, we use sequential indicator simulation, and this method was employed because of 3 reasons. Number 1 was that we had 7 wells, and this was enough control to have a good distribution across the field. The second was that it allows us to use a flexible variogram as indicated by the properties of our data. And number 3 was that it allows for a flexible understanding of simple depositional shore phase transition, and it also allows to handle heterogeneity in the reservoir, which was our objective of the project as well. So the results, the petrophysical, we use